Thanks all for coming. So I was told that there's also a combinatorics seminar happening at the same time, so I apologize for having this. It's fault's all mine. So I'll be talking about joint work with Nima Nari and Shayan Veskaran on mixing times of Markov chains for sampling independent sets. Okay, and also connections to high-dimensional expanders. Okay, so so in the field of approximate counting and sampling, there's sort of two tasks you want to solve. So you're given some non-negative function on the collection of subsets of, say, 1 through n. And you want to, the first task is you want to generate samples. You want to sample a set S with probability proportional to mu of S. And the second task is to compute this so-called partition function, which is the summation of all these mu S. So you should think here that mu is not necessarily normalized, so the summation of mu S is not equal to 1. Mu is also given to you via oracle access. So it's not given to you as like a list of all the mu S, but if I tell you some set S, you have some function that will return to you mu of S. Okay. So I guess there are a lot of like natural examples, such as like say if you want to look at say uniform distribution over perfect matchings or connected subgraphs or independent sets and so on. Okay, so a natural algorithm that people use to solve these two tasks is via Markov chain, and here's a very simple one, which is just that you select a uniformly random element I, and then you transition to one of two possible states. You either add I or remove I from your current set S. Okay, and so this is called the Glauber dynamics. And a question you're going to ask is, under what conditions does the Glauber dynamics mix rapidly? Okay, or more specifically, under what conditions is the second largest eigenvalue of its transition probability matrix bounded away from 1? Okay.
So you want to make sure that this switching is with such a probability that it's A, easily computed by a few oracle queries, and B, it guarantees that the stationary.
Yeah.
Before you get to eigenvalues, I don't know if everybody
okay.
has seen this kind of thing.
Sorry, yeah. So, yeah. So I guess so with this probability, you can show that it has the right station. It will converge. The distribution of the chain will converge to the right stationary distribution. And I guess here you only need to compute, I guess, like three. You need to query 3 elements. Make 3 queries. Okay. So I guess for the rest of the talk, it's just we'll just focus on like bounding this second eigenvalue of this of the transition matrix. Okay. 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 So we introduce one.
Again,
sorry. Yeah.
Another thing. This Markov chain is exponential size. You can just move along the sets, right? It's exponential size. Bounding this second eigenvalue will guarantee that convergence is in polynomial time.
Right, yeah. So the number of states is like 2 to the n, but you would want something polynomial in n, the size of the number of elements in your ground set. Okay. Yeah, exactly. So we introduced one such criterion. We call it spectral independence. And to define it, let me first introduce this so-called correlation matrix. So this is a matrix of pairwise correlations between elements. And okay, so what I mean by probability of J conditioned on I is if I sample a random set S, the probability of J and S condition on the event that the element I is also in S. Okay, and I bar just means the I is not in S. Okay, this is the shorthand notation. So I form this matrix.
Can we think of some specific Markov chain as an example? Maybe it'd be easier to think about.
So I guess. I mean, I'll tell you like a concrete one later, but I guess you can think maybe for sampling independent sets of a graph, the transition will look like, for the Markov chain looks like I pick a random vertex in a graph, and then I resample the assignment of whether or not it's in or out of my current independent set. Okay, does that make sense? Yeah. I'll have like a demonstration later. But, yeah. Okay, so I have this matrix of pairwise correlations, and we say it's spectrally independent if it just has bounded maximum eigenvalue. So you should think of maximum eigenvalue as somehow capturing like the total amount of pairwise correlation in this distribution.
The error of the red box is pointing only to the first probability or to the difference?
Oh, sorry, it's to the difference.
To the difference.
Yeah. Okay. So let me tell you some. Maybe I'll give you some examples. So I guess for a lot of applications, it suffices just to bound the maximum absolute row or column sum. But I'll get this later. So let's just see like some concrete examples. So suppose I have the following mu. It just assigns the value 2 to the set 1, 2, and then assigns the value 1 to the set 2, 3. Okay. And let me say also, I assume that this correlation matrix it just puts zeros on the diagonal. Okay. So let's look at these two entries. So the thing notice here is that 2 is in both of these sets. So no matter what I do with 1 and 3, like whether or not 1 and 3 are in or out, it doesn't affect the probability that 2 is in. So these two entries are 0. If I look at how 1 and 3 influence each other, if I know 1 is in, then I know 3 is automatically out. If I know 1 is out, then I know 3 is automatically in. And so I get -1 for those two entries.
So mu is not a measure here?
So you can think of it as a measure where it's normalized to, you can normalize it by the summation of all the mu's. But when you're not like, the function.
Eta will depend on the normalization of mu.
Sorry?
Oh, the eta.
Oh, this one?
Yeah.
Yeah, so I mean, since the entries are normalized, right, so they're probabilities, so they're, you can think of it as like after I've normalized it, I compute these probabilities. So, yeah. Okay, and then for the last two entries, it's just if I know 1 is in, then I know, if I know 2 is in, then it's just the probability of whether or not like 1 is in or out. Okay.
Actually, I'm sorry. S, what is it? Can you what is S in the example? It's a pair or?
Oh, sorry. So S will just be these sets 1, 2, or 2, 3. So
S is drawn from mu.
So mu is.
S is drawn from mu.
Yes.
Okay, right. So here mu has support on only 2 elements.
Yes, it's only 1, 2, and 2, 3. So let's see another example. So if mu is an independent distribution where whether or not I is in or out doesn't affect j, another element j, then this matrix is a 0 matrix, and then this distribution is 0 spectrally independent, which is like the most amount of independence you can have. Let's say mu is only supported on these two sets, okay? And they're disjoint sets, okay? In this case, if I know, say, 1 is in, then I automatically determine the status of all the other elements. So I can write down the correlation matrix is just this block matrix. And then from this, you can compute that its maximum eigenvalue is exactly n-1. Okay? And this is like the worst case. So we have two extremes, like independent distribution is 0 spectrally independent, and the other side is like n-1 spectrally independent. Okay. And a final, slightly more interesting example is, let's say mu is negatively correlated, which just means that if I condition an element to be in, it only decrease the marginal probability of all the other elements to be in. Okay. Then in this case, the correlation matrix, all the entries have the same sign. And so if I look at, say, just any row sum, absolute row sum, is like the sum of the absolute values is the same as the absolute value of the sum. And if I further impose that mu is supported on sets all of a fixed size, of the same size, then you can show that this sum is exactly 1. So in particular, this means that for such a distribution, it's 1 spectrally independent. And that's very good. So in general, you want your distribution to, say, have spectral independence that's not dependent on n. Okay, so now let me strengthen the definition a little bit to sort of encompass all of the conditional distributions. So not only do I want my distribution to be, say, eta 0 spectrally independent, but I also want all conditional distributions based on, conditioning on one element to be eta 1 spectrally independent. By condition on two elements, I want to be eta 2 spectrally independent, and so on. Okay.
Condition on both in and out.
Yeah, like.
So like 4 conditions for 2.
So.
Like in, out, etc.
Yeah. So any possible set of conditionings. Yeah. Yeah. Okay. So our first result says that basically if I have spectral independence for all of these distributions, then I can get some concrete mixing time for the Glauber dynamics. Okay, so if you want polynomial time algorithms, you really want this alpha, the spectral independence parameter, to be independent of n. Okay. So now let me introduce sort of our main application, which is to the hardcore model. So the hardcore model is a distribution on independent sets of some input graph, where I get to weight each independent set by some parameter lambda to the power of the size of the independent set. Okay, and so here the corresponding partition function is this summation. So just give you an example for this graph. I always have the empty set as an independent set, so that gives me the constant term 1. I have 4 vertices, that gives me 4 lambda, and I have 3 pairs of vertices that are not connected by an edge. They give me 3 lambda squared, and then I have this large independent set here. It gives me lambda cubed. Okay. And so exact value evaluation of this partition function is sharply hard, even for very restricted classes of graphs. Okay. So we aim for sort of efficient approximation algorithms. So I guess, why have people studied this? So this sort of arises as like some model of like gas particles. It's also used to like model communications and networks, and also has connections to like other models in statistical physics, such as the Ising model for magnetism. And sort of an interesting aspect of this model is that it exhibits so-called like some kind of phase transition, has like phase transition properties. So let me describe this a little more concretely. So let's say I look at the hardcore distribution on this tree, okay? And let's say I root it at some vertex r. So I'm going to use green vertices to denote that my vertex is conditioned to be in the independent set, red vertices to denote like it's out of the independent set, and then white vertices just unassigned. Okay, so let's say, so I want to look at the marginal probability that the root is in a random independent set. So if I condition a neighbor to be in, that automatically forces my root to be out. Okay? So in particular, it decreases its marginal probability. I can look at vertices that say 2 steps away. If I condition to be in, then the corresponding child is out, and you can think of this as putting fewer constraints on the root. And so this will in particular increase the marginal probability of the root. Okay. And I can do this more generally. I can condition a whole bunch of vertices, let's say distance 3 to be in, and this will drive down the marginal probability of the root. Okay. So you sort of notice that there's this kind of dependence on, so how these conditionings affect the marginal probability of the root. It kind of depends on the parity of the distance. So if I'm at odd distance away, and I condition them to be in, this will decrease the marginal probability of the root. If I'm at even distance away, this will increase the marginal probability of the root. Okay? But sort of what you would like to say is that this effect on or this dependence on the parity should sort of go away as the distances go to infinity. Okay? And so this is true only for lambda smaller than a certain threshold, which is this sort of critical threshold. And sort of above it, this dependence sort of persists even as you go to very large distances. Okay, and this is sort of this phenomenon called correlation decay, which I will describe more rigorously later on.
You did say that delta is the degree of the graph.
Sorry, yeah, okay, yeah, that's a good point. Yeah, so here delta is the delta for the maximum degree of the graph. So, yeah, that's a good point. Yeah. Okay. But so the significance of this threshold. So also a lot of theoretical computer scientists sort of conjecture that this thing also corresponds to some kind of phase transition in complexity, so to speak. So for lambda above this threshold, you should get hardness results. Even like it should be hard to even approximate the partition function. And below it, you should have efficient algorithms. Okay? So I'm show you like sort of some prior works just for mixing of the Glauber dynamics.
So maybe just for intuition, I mean, this is about constant over the degree. That's a lambda. And lambda just weighs independent sets by the, it just gives weight to the independent sets. So this will be, you prefer independent sets that are small.
Right, exactly.
It's not about counting big independent sets, it's about counting small independent sets.
Right. So.
And with 1 over d, you will be counting independent sets roughly about, what the greedy algorithm would give you.
Right.
But it's about one, you just pick a vertex and throw its neighbor. So it's
right.
sort of the easy regime. I mean, that sort of
right.
goes
Yeah.
well with what you were just describing. So for intuition, we are just, I mean, it should be easy roughly at that range.
Yeah.
Because the greedy algorithm can at least find an independent set like that and maybe
right.
fully count it.
Yeah. Exactly. Yeah, that's a good intuition. And also, I guess, for if you have lambda very large, then you're preferring large independent sets, and we know that finding maximum independent set in a graph is hard to approximate. So there's sort of, this. Right. So let me just mention some prior works on like establishing mixing times. So this was studied very early on by Luby and Vigoda, which showed that if you have lambda less than, say, 1 over delta maximum degree minus 3, then you can get rapid mixing. And sort of many works that sort of improve on this. But sort of getting to this exact critical threshold, people can do it without making further assumptions on the graph. So you either have to assume that there were no short cycles in the graph, or the graph is of, say, some sub-exponential growth or something like this. And on the hardness side, people knew very early on also that this constant over delta, there should be some above which there should be it should be hard. And the works here sort of just slowly refine it to get to exactly this critical threshold. And this was finally done in the work of Sly in 2010, which showed that there is no efficient approximation algorithm above this threshold unless p equals np.
But also we know algorithms that are efficient and are not Glauber dynamics.
Yes. Okay. Yeah. I was gonna mention that in a second. Yeah. Based on Glauber dynamics. Yeah.
So exactly what is the Sly result? Sly result is about Glauber dynamics or about any algorithm?
Sorry. Yeah. So Sly's result is for no algorithm. I guess there was a prior work that showed that Glauber dynamics doesn't work. And I guess let me also just mention that there are also, this problem is also interesting for restricted classes of graphs, like random graphs or lattices and so on. So as I mentioned earlier, there's this hardness result for lambda above the critical threshold. There's no efficient approximation algorithm by Sly, and by further refinements, and with further refinements by Sun and Galanis and Stefankovic and others. And then there's this great work of Weitz in 2006, which using not the Glauber dynamics, but this other deterministic correlation decay algorithm that gives you efficient approximation on bounded degree graphs below the critical threshold. Okay. But sort of one not so great aspect of this algorithm is that it has an exponential dependence on log of the maximum degree. Okay, and this seems somewhat inherent to the algorithm itself. Okay, so what we show is that the Glauber dynamics mixes for all lambda less than the critical threshold with no dependence on the log of the maximum degree in the exponent, and with no further structural assumptions on the graph. Okay. So in this work with Nima and Cheyenne, this constant c of little delta is a little bit horrible. It's exponential of 1 over little delta. But in sort of follow-up work with Eric Vigoda and his students, we have brought this down to 1 over delta, and this is tight. Okay? And we also have some generalization for all antiferromagnetic two-state spin systems, but I won't talk about that. Okay. All right. So more specifically, we show that we have spectral independence for the hardcore model, and then if you add on the previous result I mentioned, which is that spectral independence implies mixing, then this is exactly the result. Okay. So this talk is split into sort of 2 sections that are like logically independent of each other. So if you can sleep through one of them and sort of get back on track in the other one. And yeah. Okay, so let me talk about, I guess, the second part first. And this part goes through the, okay, actually first let me see, are there any questions? Okay, so this part goes via this sort of connections with high-dimensional expanders. Okay, so basically the main point of this section is that sort of using simplicial complexes, we can use this as a way to decompose this exponentially large Markov chain into a bunch of little ones. And okay, so what is a simplicial complex? It's just a downwards closed family of subsets of, say, 1 through n. So for our purposes, we'll model it as follows. So if my distribution mu is supported on subsets of 1 through n, then my simplicial complex will have ground set 1 through n, and then 1 bar through n bar, just meaning in or out, indicating in or out. And then each set in the support of mu will correspond to a maximal face of this, or a maximal set in this simplicial complex, just by for those I that are in S, I think of each set S as some indicator vector. And then for I in S, I put I, and then for I not in S, I'll put I bar. So just a quick example, I have these vertices, and I'm looking at a distribution supported on subsets of 1, 2, 3. Then for, say, the set 1, 2, I'll put 1, 2, and then I put 3 bar, indicating that 3 is not in the set. And I can do this for any other subset of any other set in the support of mu. Okay. Okay. So let's see. Okay. So I'm going to draw like another way to look at this thing, and let's look at what it looks like for the hardcore model. Okay. So for, let's say I'm looking at independent sets of this graph. So here I have, say, an independent set for 2, 3, 4, and this is indicated by 1 bar saying that the vertex 1 is not in the independent set, and I have 2, 3, 4 for the rest of them. And then I can do this for all the independent sets of this graph. And if I take downwards closure, I'll get partial assignments on 3 vertices, indicating some of them are in and out, and then some of them are undetermined. And these edges, these edges just indicate like which face is contained in which face. Okay, so now I want to tell you how I can realize the Glauber dynamics in this framework, or as like a sort of very natural motion on this simplicial complex. Okay, so let's say I start at some independent set. Okay, let's say I start at the biggest one, and so the Glauber dynamics tells me that okay, I'm going to sample vertex, I'm going to resample its spin. So first, I can think of it as I first unassign that vertex, and this corresponds to a down motion in the simplicial complex. And then I resample the assignment for that vertex, and then I go back up. And this sort of down-up motion corresponds exactly to this Glauber dynamics. That's the main claim. Okay, so I guess I can just sort of keep going. Okay, so Okay, so now basically what I'm really doing is I'm decomposing this large up-down or down-up kind of motion in the simplicial complex into a bunch of smaller ones that I'll tell you right now. Okay, so so let me tell you what the local view of say some assignment in this simplicial complex looks like. Okay, so so let's say I'm looking at, let's say I haven't made any assignments yet. Okay, and I'm going to look at this sort of local graph, which is just defined on vertices and edges. Okay, so I think of this as like essentially I'm looking at sets of size 1 in the simplicial complex as vertices, and then sets of size 2 as edges connecting these vertices. Okay. So let me first tell you what non-edges are. So obviously I cannot assign both in and out to the same vertex. So I won't have an edge connecting 1 and 1 bar, 2 and 2 bar, 3 and 3 bar, and so on. But also I won't have these edges because I can never have, say, 1 and 4 both be in the same independent set. Okay. But then everything else is allowed. Okay, so this is the unweighted version. But OK, so now I need to weight things just so I have like, the right distribution. So the way I weight things, weight these edges, is by the total number of independent sets that are consistent with this edge. Okay, so what I mean is, so let's say I look at the vertex 1 and then 4 bar. I look at all independent sets that have 1 and don't have 4. Okay, and then I just add up their corresponding weights. Okay, so for here, there was only one independent set, which is just 1 itself, and so I'll get weight lambda, and I do this for every other edge. And I'm not going to draw like all of them, but this is roughly what it looks like. Okay, does this make sense so far? Okay, so now the key thing is that, okay, so that was sort of what this thing looks like from the perspective of the empty set. Okay, I essentially just ignored all of the sets in the simplicial complex that are size larger than 2, and I just look at these are my edges and these are my vertices. Okay, but I can have the same local view from any other set in my simplicial complex. So I can say look at, and this corresponds exactly to say first conditioning on some assignment, and then looking at the corresponding simplicial complex, and then the local view from the bottom. Okay, and I can do this for any set in this simplicial complex. Okay. So now these are essentially what these all these small chains are, which is just look at the local view and look at the corresponding random walk on that small graph, weighted graph. Okay. Okay. So I have all these small chains. Now I need to tell you how it is that if I have good, like say, fast mixing on all these small chains, how this implies fast mixing of this large chain that I really care about at the end. Okay. Okay. So let me first tell you what it means. Let me tell you what it means for like all these local chains to have fast mixing, which is just they have good second eigenvalue. Okay. So I just want that for every. So we say this simplicial complex is a local spectral expander if all of these small chains, these local random walks, they have bounded second eigenvalue. Okay.
What does it mean really if it's disconnected? It's lambda 2. I mean, this graph may be disconnected.
Right. So it turns out, so if any of these local chains are disconnected, this will actually imply that the global chain that you care about is also disconnected. Yeah.
It will be if the local chain is disconnected, then the global one is
also disconnected.
Because you added these complements, that's the reason it's not clear to me, but I guess I believe you.
Oh, okay. I see. I guess. Yeah.
Why do
2 in case of sometimes lambda 2 is meant to be the second eigenvalue of each connected component is small. But so I just want to understand the definition.
Oh,
Okay.
yeah, okay, so lambda 2, it's an adjacency matrix with 2n by 2n vertices, or?
Yes.
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 Yes, and it could be connected this way, otherwise.
Yeah, it will be connected.
Otherwise, the big chain will not.
Right. Yeah.
I don't see that, but I believe that.
Oh, okay. Okay, maybe we can talk offline. Yeah. Sorry. Yeah. Okay. So, right. Okay. So let's say I have some kind of local spectral expansion. So let me tell you quantitatively what kind of a bound.
Let me just so
Mm.
this condition is again you want it for all subsets.
I want it for everything.
So
Yeah.
you want lambda 2 to be small for all the subsets. All
Right.
the subsets will be connected. That doesn't make sense.
All the subsets will be.
All the subgraphs, all the induced subgraphs of this graph will be disconnected. They will be connected.
So I mean, they're not subgraphs of each other. They're more like, yeah, they're not subgraphs of each other.
Subgraphs of each other. Right?
Yeah.
They are just for the conditional distribution.
Right.
But they will also be, all of them will be connected.
Yeah.
Yes, you need all of them.
Yeah. Okay.
I mean, disconnectivity will happen at that level. It could still be that one skeleton is like a complete graph, but you still can be disconnected at higher levels.
Yes. Okay. All right. So let me just say. Okay. So now let me tell you more concretely how these local eigenvalues will imply like a global bound. Okay. So this sort of local to global phenomenon was already observed in many previous works by Kaufman.
Can you show the previous Porto theorem
Sorry?
what does it say?
So it just says that if I have a bunch of local eigenvalues that are good, then the thing you care about at the top is also good. So this sort of local to global phenomenon was already observed in many previous works by Kaufman-Mass and Deneuer-Kaufman and Oppenheim. But we'll sort of use the most recent refinement of these results, which just says that if I have all these, I get this sort of nice expression for the second largest eigenvalue of the global walk at the top. Okay. So just think that here that if alpha k's are bounded by, say, some constant over n minus k, then you get 1 over n to the power c, that constant for your second eigenvalue. Or a spectral gap, sorry. Okay. So roughly the proof strategy is just that if I have local spectral expansion and I plug it into this local to global theorem, then I'll get rapid mixing. Okay. Okay. Wait, sorry, I actually forgot to ask, like, how much time do we have? Or
Oh, an hour moment?
okay.
We still have 25 minutes.
Okay, sounds good. Okay, okay. Okay, so now let me tell you sort of this piece of it, because the local global theorem was already proven by Vedat-Levy-Alev and Lapchi-Lau. Okay, so I want to compare what this weighted random walk matrix on this local graph looks like with this correlation matrix that I've defined. Okay. So the main claim is that the second largest eigenvalue of this random walk matrix is exactly the maximum eigenvalue, normalized by 1 over n minus 1. Okay. All right. So you can show, if you compute it, you can show that the entries of this local random walk are exactly these conditional probabilities, right? Because essentially the weight of an edge is just the total number of the sum of all the independent sets that are consistent with this edge, and then the weight of a vertex is just the sum of all the independent sets that are consistent with this vertex. And so if you normalize it correctly, you get exactly this conditional probability. Okay? And if you recall that my correlation matrix is just this difference of conditional probabilities. Okay. So basically, what happens is, okay, I can write down this correlation matrix as exactly this sort of projection of this my local random walk matrix. And why is it that these eigenvalues there's this identity of eigenvalues? Is exactly the reason that this this projection sort of kills off all of the so-called trivial eigenvalues of your random walk matrix, right? So the nice thing you have to notice about this is that there's this nice structure for this local graph, which is that it's sort of these n distinct parts where there are no edges between them. And what this sort of induces large multiplicity of this particular eigenvalue in this local random walk matrix. And so if you sort of project away from all of those eigenvalues and those eigenvectors, you get exactly this correlation matrix. Okay? So that's roughly how you prove such a thing. Okay, so that concludes the first part. Are there any questions? Or I guess the second part. Yeah. Okay. So now I'm telling you about something more specific to the hardcore model, which is now, I just need to bound this spectral independence parameter for the hardcore model. Okay. And we do this sort of by connections with this correlation decay, and which I'll tell you about more in a moment. But first, let me say how. So there are previous approaches to bounding these like local eigenvalues, and the main result there was this result by Oppenheim using so-called Garland's method, which tells you that if I can show some nice eigenvalue bound at a higher level in the simplicial complex, that this will imply second eigenvalue bounds at lower levels. Okay, so if I have lambda, say, for all distributions conditioned on a single element, then this will imply a corresponding second eigenvalue bound for the distribution itself. Okay. But so the crucial thing is that this bound deteriorates as you go down the simplicial complex. So at higher levels, you need a very strong bound at the top in order to get anything non-trivial at the bottom. Okay. But in practice, what you tend to observe is that eigenvalues are actually very bad at the top, and they improve as you get to the bottom. So at the top of this simplicial complex, you're essentially looking at independent sets of a constant size graph. And so the eigenvalues of such a local random walk cannot be 1 over n. They're like a constant. Okay? And at the bottom, what you expect is actually 1 over n, roughly. Okay? So we cannot use such a trickle-down theorem, so to speak. Okay, so now let me show you how we use this so-called correlation decay. So let me first formalize correlation decay as just, if I look at this sort of pairwise correlation, this is exponentially small in the distance between the vertices. So I'm thinking so J and I are like vertices of my graph. The distance is just the graph distance. And what I'm saying is that if my two vertices are very far, then whether or not one vertex is in the independent set should not affect very much the marginal probability of the other vertex being in an independent set, depending on how far they are.
It's a theorem.
So this is a definition, but we know that it holds exactly when when we're below this critical threshold. Okay.
Okay, so you define mu to be weak spatial. Who is being defined here? Mu?
So yeah, mu satisfies weak spatial mixing. If these corresponding, yeah. Okay, this is not exactly weak spatial mixing. It's a little bit stronger than this, but I'm just showing you for the just pairs of vertices, because that's all we need. Okay. Okay, so let me just say that so first let me show you that for like say certain types of graphs, this will already give you like an interesting bound. So if I assume, say, I'm working on only the lattice, okay? So I can bound my maximum eigenvalue by just the maximum row sum. And now I can sort of split my vertices into like levels, so like different, I guess like different balls of different distances, different radii. And I can just apply weak spatial mixing, which we already know holds for lambda less than the critical threshold, just in like a black box fashion. And so we get that the point is that for a graph such as the lattice, these balls only grow polynomially fast. Whereas since I have spatial mixing, I know that these correlations are decaying exponentially fast. And so such a thing will always be bounded by a constant or a 1. Okay? So in particular, so any graph of sub-exponential growth, you can immediately use this to deduce fast mixing. Okay? But sort of the main challenge is that for most graphs, they're obviously not like expanders. They're not growing so slowly. Okay? So the rough strategy is to sort of go back into the proof of weak spatial mixing and sort of readapt it to the situation where you have, graphs that are growing not sub-exponentially fast.
But
Okay.
is it true that, last kind of logic, if the graph is more expanding, you expect to be even more mixing, right? So
Not necessarily
Not-
the independence.
I'm not sure if you expect it to be better in that case.
because because it's the independent sets in this graph that you're.
Yeah, you're looking at independent sets. Yeah.
It's not the Markov chain that's expansive.
It's
the graph.
It's the graph of the independent sets. So that's
Yeah.
Just false what I said. Okay.
Okay. So roughly the way a lot of these proofs work is that you sort of reduce the problem to a problem on trees, and then you try to solve the problem on trees. But and this sort of can be done in like a black box fashion using the previous work by Weitz, and I won't get into like how to do this like tree reduction. So I'm just going to assume that suppose I have some rooted tree now, and I want to bound like the total amount of, you can think of this also as influence, like the influence of all the vertices below it to the root. Okay. Okay. So the way to sort of analyze this problem on trees is that there's this nice recursion for computing the marginal probabilities for a tree. Okay. So if I have a graph, I can always, so the first observation is that if I have any graph, I can always break up its partition function into two smaller partition functions, one where I've conditioned my vertex to be in, and the other one where I condition my vertex to be out. Okay? And a nice thing for trees is that, well, if I condition the vertex to be in, this sort of breaks my graph into, this connects my graph into a bunch of smaller subtrees. Okay? And so I can write out sort of a nice formula for the marginal probabilities. Okay? So it just sort of looks like this ugly expression. And this thing, so this expression also holds if I condition on any vertex, below. Okay. Okay. So using this sort of tree recursion, I can sort of the first approach you would try is just like bounding each pairwise correlation separately. So I claim that if I look at, say, the root and some vertex below, that this pairwise correlation is bounded by, say, just lambda to the power of the distance. Okay. And the proof is just sort of pretty straightforward using this tree recursion. Okay. So what I can do is I look at this pairwise correlation. I sort of expand it out using the tree recursion. Okay. And I put sort of common denominators and the such, and I pull out. Then you get a constant factor in front times something that's less than 1. Okay. And if you just sort of keep inductively unrolling this all the way down, you get exactly lambda to the power of the distance. Okay. And also, this bound is essentially tight for some graphs. So, for example, for a path, this is exactly this bound is tight. Okay. So. Okay, so now you can ask, like, okay, well, if I have such a thing, what would it imply? So if I have my graph is at maximum degree delta, I can have as many as delta minus 1 to the power d many vertices at distance d. Okay? So if I just plug in this bound, immediately I will get this expression. I get like a sort of this infinite sum. It's always bounded by this infinite sum. And this infinite sum is bounded by order of 1 exactly when lambda is less than 1 over maximum degree. Okay. Okay. So this is not exactly the critical threshold. And roughly speaking, it's kind of like this bound is only tight for graphs that look kind of like a path. But for a graph that has that many vertices at distance d, it should not look anything like a path, right? So that's sort of where instead of 1 over maximum degree, you can sort of gain a little bit to get to the critical threshold. So basically, the final strategy is to sort of amortize over all the vertices at a given distance. Okay. So roughly speaking, what you can show is if I look at the total correlation of vertices at a given distance d with the root, this entire thing is contracting as I get farther and farther away. And the rate of contraction is sort of governed by this, you can show it's related to the norm of the gradient of this tree recursion. Okay? And using prior works, you can show that exactly for lambda less than the critical threshold, this gradient, this norm is bounded by 1. Okay, it's strictly smaller than 1.
So what is capital F?
Oh, sorry. Okay. Okay, I didn't write. Okay, so F is. So I have this. I guess I have this tree recursion at the top. As I think of it, F is just. It's like so the marginal probability of the root is like a function of the marginal probabilities of its children, and you can think of this as like a function taking with input just the marginal probabilities of the children, and it will compute the marginal probability of the root. Okay.
So it's for a regular tree?
I'm sorry?
It's for a regular tree, or F is a function just it's different functions at different vertices?
Right, so you can think of, so F is like this, is a multivariate function, and I can plug in different values for the marginal probability.
But in different vertices there may be a different number of neighbors, so it's a function that depends on the degree.
Right, but I can if a vertex, they might have different number of children, but if I can sort of pad it with a bunch of like 0 children. Make sense? Okay. Okay. Sorry. Yeah, I mean, okay. So I'm also kind of lying to you a little bit here. I mean, it's not really the function itself, but you sort of have to add certain like a potential function and so on. But morally, this is like roughly what's happening. Okay. Now, if you just sort of apply such a statement, then you get exactly the right result, which is just that I can bound all of this total amount of correlations by roughly 1 over delta. Okay. And so only for technical reasons, in our original proof, we can only get exponential of 1 over delta. Okay. Okay. So roughly so that concludes the second part. Any questions? Okay. All right. So let me just remind you sort of the rough proof strategy for getting mixing. If you're interested in, proving new results for Markov chains, basically we have this local to global theorems, and you want to prove a local spectral expansion kind of statement. And so we have some tools based on what I showed you, which is like correlation decay and spectral independence, but also trickle down theorems, also Hodge theory, and so on. But I think we still need more tools that that will help us analyze many other classes of distributions.
What's the Hodge theory?
Okay, this is just one tool you can try to use to establish this. I'm not going to describe what Hodge theory actually is, but.
Yeah, but what's the name of the people that?
Okay, so.
This guy.
Yeah. Well, okay, so I guess Hodge theory for matroids, or for a certain class of objects, Hodge theory was proved by various people. So for matroids, it was by Adiprasito, Juni He, and Katz, and various others. Or for other Hodge theories, there are other people who've also proved kind of statements for it. But yeah, I'm not going to get into what it is. Okay, so I guess let me just conclude with some open problems, which is just new ways to establish local spectral expansion, or maybe explore other distributions where you can get mixing this way. And then more specifically for the hardcore model itself, it's believed that, so we have n to the 1 over delta essentially for mixing, but it's sort of believed that you can get actually much faster, like n log n. Okay. In sort of follow-up work with Eric Pagoda and Dongchen, we get this for bipartite graphs, but sort of the general graphs case is still open. Okay. But yeah, that's it. All right, thank you.